All right, so this video is going to go over the pages 6 through 8 in your circular motion packet. So we're going to talk about frequency and period again. Okay, so remember those two are different. Frequency, we're going to start off with a symbol F, lowercase f, and your period is going to be a capital T. Now, period is the time it takes for one revolution. So time for one revolution. Okay, so while it is a time, we're not going to use lowercase t, okay, because time with lowercase t is just time in general, while uppercase T is actually specific to circular motion because that's the time it takes for one revolution. So you may see some questions that have a time in there, but that is not necessarily the period, so you just got to be careful with that. And frequency is going to be the number of revolutions per second. Okay, so how many revolutions were there in that 1 second of time? Now your units for frequency is going to be hertz. Okay, so, and then your period is going to be time, which is going to be in seconds. Now your equation for frequency is going to be F equals 1 over T. And since they are inverses of each other, technically T equals 1 over F. Now there's also other ways to find period and frequency. Okay, so one thing we talked about in the last unit or the last pages was if I give you a certain amount of time and a number of revolutions, you can take that total time and divide it by the number of revolutions, and that'll tell you the time it takes for one revolution. Now, frequency is going to be the opposite of that. You would take your number of revolutions and divide it by your time. Now, linear speed or tangential speed is the distance of the object moves around the circle over time. So linear speed is technically V equals D over T. Okay, but now since we're talking about circular motion, okay, we're going to talk about our distance is now our circumference, so which is going to be 2 pi r, and your time is going to be your capital T, your period. So we're not necessarily going to really use this d over t, we're going to use that circumference over your period. Now, definition of centripetal acceleration, that is just acceleration experienced in circular motion by changing direction. I'm not going to worry about writing that down. You've got the definitions on the previous video. Okay, so your symbol is going to be AC, and then your equation is going to be AC equals V squared over R. Okay, just be careful with these equations. It's real easy to get T and R in the wrong spot, or you forget to square something. So just make sure you take your time and set things up correctly. So the first practice says, what is the centripetal acceleration of a car? So we're looking for AC. With a velocity of 25 meters per second, so there's your V, is going around a curve with a radius of 25 meters, so there's your radius. And I did give you a time of 2.75 seconds. Now, if you notice, it mentions just going around a curve. That's technically not a full circle. So I'm not going to say this is capital T. That's not going to work. Okay, so we're going to look at what we have, because if we're looking for AC, AC equals V squared over R. I have V, I have R, so technically that time doesn't do anything. So if you don't need it, don't use it. Okay, so I'm going to do V squared over R, so 25 squared over R, which is 25, and this is going to just come out to be 25 meters per second squared, and that's your answer. Number 2, what is the centripetal acceleration of a stone being rolled around in a circle at the end of a 1.5 meter string? So we're looking for AC. We have our radius, and I gave you 16 revolutions every 8 seconds. So this is not big T. Okay, that's your total time. That's not the time it takes for one revolution, but we can find it, okay, because we know our period is the number of seconds, which is 8, divided by the number of revolutions, which is 16. So divide that and you get 0.5 seconds. So that means it takes 0.5 seconds for one rotation. Now, you're looking for AC. Remember, AC is V squared over R. So do we have V? No. So we need to find it. So what we're going to do is we're going to do V equals 2 pi R over T. So we're going to plug in. So 2 pi, my radius is 1.5. And my period we just found is 0.5. So you're going to do that math and you should get 18.85 meters per second. Now we have our velocity. Now we can bring it over here and plug it in. So we're going to take that 18.85 and we're going to square it and divide it by our radius, which is going to be 1.5. So this is what I mean by be careful, is a lot of times you'll see students that will take that 0.5 that's on bottom right here, and they just assume that goes on bottom again, okay? You got to look at, is the bottom for the V equation is T. The bottom for the AC equation is R. So those are different, so just make sure you're not making that simple mistake. It's easy to do, okay? So 18.85 squared divided by my 1.5, and you get an acceleration of 236.88 meters per second squared. Now we're going to go on to the next page. So this is kind of going to be redundant. Again, this is a short unit, so we want to make sure everybody's on top of their stuff. So period, again, is the time for one revolution. So time for one revolution. Now the formula period we're starting to learn is you can calculate it different ways. Okay, you can do T equals 1 over F, or you could take your total seconds and divide it by your revolutions, or you can even solve for it using the V equals 2 pi r over T. So that'll bring us to our next one, is if we reverse the equation for formula velocity, what's it going to look like? So we know V equals 2 pi r over T. Well, remember, we can switch these components back and forth. So that's technically saying the same thing as T equals 2 pi r over V. Okay, so if you're looking for T and I give you R and V, you can do that as well. The point is there's lots of ways to find period. You just got to look at what you have. If you have frequency, just do 1 over F. If you don't have frequency, then you can't do that. Okay, so you just got to make sure you look at what you need. So rotational speeds are often written in RPM, so that's rotations per minute. But in physics equations, we must use units of velocity, which is meters per second. So how to find our period if you know RPMs? So there's 60 seconds in a minute, so we can find our period by taking 60 seconds and dividing it by the number of rotations per minute. Okay, so there's another equation on how to find T. So there's lots of ways you can do it. You've got this one here, you've got this one here, you've got this one here, and you've got this one here. So it doesn't matter which one you use, it just matters what you have. Okay, if you don't have some of those, that means you can't use all of these. It just depends on what you have. Now, linear acceleration is technically A equals V over T, but we're not talking about linear, we're talking about circular, so we're not going to really be using this. We're using the whole AC equals V squared over R. Now, a wind turbine with a radius of 6, now in this black picture, there's supposed to be a wind turbine in there, but printers just didn't do too well on this. A wind turbine has a radius of 6 meters, there's your R, is turning at a rate of 16 RPMs. So find the period. Well, we know T equals 60 over RPMs, so 60 over 16 is going to give you 3.75 seconds for your period. And there's your answer. B, find the speed in meters per second of the edge of one of the blades. So remember, you got to know that speed is velocity, that is not acceleration. So you're just going to do V equals 2 pi r over T. So 2 pi times my R, which is 6, all over my T, which is 3.75. And our mass should come out to be 10.05 meters per second. Number 2, the edge of a fan blade is moving at 150 meters per second. That is your velocity. The blade has a radius of 0.3 meters. There's your radius. Find the period. So you got lots of options to find period. I don't have frequency, so I can't do 1 over F. I don't have time, and I don't have revolutions, so I can't do time over revolutions. And I don't have RPM, so I can't do that. But remember, we know is V equals 2 pi r over T. So 150 equals 2 pi times my radius, which is 0.3, all over T. So all you got to do is just switch these two and take 2 pi times 0.3 and divide it by 150, and you get a time of 0.013 seconds. So that's your period. Now it says how many RPMs are there? Well, if I know T equals 60 over RPMs, I can take this 0.013 equals 60 over RPMs, and I can just switch these two. So 60 divided by that, and you're going to get 4,615.38 RPMs. Now again, if in this case I kept it to the thousandths place, if you rounded different, okay, as long as your math's good, you don't have to really worry about that. So if you said 0.01, that is going to give you quite a different answer. But as long as you can back it up with your math, I'm not going to really worry about the rounding in this case. So as long as you do the steps. Now, a record player spins a standard 12-inch diameter vinyl records at a speed of 33 1/3 RPMs. Write the radius in meters. Okay, first thing I notice is it says diameter. Okay, the only time you really need to pay attention to the word diameter, because if we always use radius, that means I've got to fix that. So 12 divided by 2 gives me a 6-inch diameter. Now, I need to get to meters. I'm in inches, and I just told you that there's 2.54 centimeters in an inch. So I'm going to do is I'm going to multiply that 6 inches by 2.54, and that gives me 15.24 centimeters. Now, I need it in meters, and we know there's 100 centimeters in a meter, so we're going to divide by 100, and that's going to give you 0.1524 meters. So just be careful with that. If you need to check, if you decided to multiply by 100, now all of a sudden you have a 1,500 meter wide or radius for a record. That's almost a mile long, so that should make sense. So just be careful with that. B, what is the period of this rotation? So remember, we know T equals 60 over RPMs. So 60 over 33.3. And you get a time of 1.8 seconds. Now, how fast in meters per second is the outer edge of the record moving? So outer edge just means you're at the max radius. Okay, so we're going to do our velocity. So velocity equals 2 pi. Radius is 0.1524 over t, which is 1.8. And you get a velocity of 0.53 meters per second. Now, part D, there's a reason why center is underlined. If you are at the center of a record, you have a radius of 0, okay? And if your velocity equation requires a radius, if you plug in 0 for r, that means your velocity is going to be 0 as well. Okay, you can be spinning around, so you could be spinning around and around, but technically you're not covering any distance, so therefore you don't have a velocity, so your velocity would be 0. Part E, what is the magnitude of centripetal acceleration at the edge of the disk? So we're back to the edge. We're no longer in the center, so E is not 0. Okay, don't get too hung up in the word magnitude. It just means value. It's basically saying what is the value of the centripetal acceleration. So in short, we're just looking for centripetal acceleration. So we know AC equals V squared over R. We know V is 0.53. We're going to square that over our R, which is 0.1524 meters. So take that, and you should get 1.84 meters per second squared. Okay, so we're going to move on to page 8. So CD player spins a standard 5-inch diameter disc, plastic disc at a rate of 210 RPMs. Write the radius in meters. So kind of like the problem we just did. So diameter, can't do anything with that. So 5 divided by 2 gives me 2.5 inches. Okay, and there we're going to multiply that by 2.54 centimeters. And that's going to give me a total of 6.35 centimeters. But I need meters, so I'm going to divide by 100. So that gives me a radius of 0.0635 meters. B, what is the period of this rotation? So T equals 60 over your RPM, so 60 divided by 210. And we're going to get 0.29 seconds. C, how fast in meters per second is the outer edge of the CD moving? Okay, so we're looking for velocity. So velocity is 2 pi times your radius, which is 0.0635 over t, which is 0.29. Okay, and we should get a value of 1.38. Let me fix that. 1.38 meters per second. D, what is the magnitude of the centripetal acceleration at the edge of the disk? So we're just looking for AC. So AC is V squared over R, so 1.38 squared over R. And our radius is 0.0635. And you get an acceleration of 29.99 meters per second squared. 5, the Earth has a radius of 6.378 kilometers and spins at a rate of once every 24 hours. Write the radius in meters. So there are 1,000 meters in 1 kilometer. So you're going to multiply that by 1,000, which is going to give you 6,378,000 meters. Okay, so again, that is just the radius of the Earth, and that's from the core. Okay, so that's going from the center of the Earth to the outer edge. We're not talking about actually covering the outer surface of the Earth, which would be quite a bit more. Okay, so there's our radius in meters. Now your period has to be in seconds. Okay, we know there's 24 hours in a day, so 24 hours times, there's 60 minutes in an hour, and then there's 60 seconds in a minute. So 24 times 60 is going to give you a time of 86,400 seconds. So there's your period. If you're at the North and South Pole, what is your rotational speed? So again, if you're at the North Pole, you're up here, or the South Pole, you're down here, and your Earth is spinning this way. Okay, so that means you were at the center. So you're basically have a radius of 0. So if your radius is 0 meters, Therefore, your circular velocity would be 0 meters per second. Now, if you're at the equator, which now you're at the equator, so you're at the outer edge, so you're at the very furthest, you're at full radius. If you're at the equator, what is your rotational speed? So V equals 2 pi. My radius would be 6,378,000 over your time, which would be 86,400 seconds. And you're going to get a velocity of 463.82 meters per second. Now, E, what is the magnitude of centripetal acceleration at the equator? So that means AC equals V squared over R. So 463.82 squared over your radius, which is going to be your 6,378,000. That's going to give you the acceleration of 0.034 meters per second squared. Now, it says explain why you weigh less at the equator. So pretend you are spinning an object on a string, like a ball on the end of the string. Okay, what's holding that ball in that pattern or that path is the string. Okay, so pretend that string is gravity. Okay, gravity is a value of 9.8 meters per second squared. Okay, now that ball is also experiencing some acceleration. So pretend if you were to cut that string, where would that ball go? Well, it would launch off, right? Okay, so that ball does have some acceleration, but as we can see here, it's very small. So you're basically being flung off by the Earth. Okay, so the Earth is trying to spin you off, but thankfully 9.8 is bigger than 0.034 meters per second squared. So I've even looked this up, is at the North Pole, if you were to weigh something like 200 pounds, at the equator, you would weigh about 198. So it's not a huge difference. Okay, but because that Earth is trying to fling you off, okay, that's basically fighting that gravity that's trying to pull you in. Now, luckily, gravity is going to win that one, but there is some that is being alleviated from that actual circular velocity. So that is why you weigh less, is because basically the Earth is trying to throw you off, but luckily gravity is keeping you on. And that'll